Okay, here we have a non-conducting charge sphere of radius big R. The charge density, that is the charge per unit volume given by rho, and we're going to allow this rho now to vary with R. We'll make it look something like so that the charge density increases linearly from the center. At the center there's no charge, then charge density is 0, and at the edge at R equals big R, the charge density is rho naught. So we have a charge density that increases linearly with R. The first thing we want to do is to find the amount of charge contained within this non-conducting charge sphere. So I'm going to write an expression for dq will be equal to the charge per unit volume times the volume. The charge per unit volume is rho naught, and the infinitesimal volume that I'm going to use will be a spherical shell whose area is 4 pi r squared and whose thickness is dr, and so that will give me an infinitesimal of volume. And I want to integrate both sides. 4 pi rho naught over r. I have the integral of r cubed dr from 0 to big R, and that of course gives me r fourth over 4. The 4's cancel. This gives me r cubed. So I have a total charge of pi rho naught r cubed, and that is dimensionally correct because rho naught has units of charge per volume. I'm multiplying volume, so that's the total charge contained within this non-conducting charge sphere. Next, I want to find the electric field at an R which is greater than big R. So I'm going to use a spherical Gaussian surface of radius big R. And again, the first thing that I always do is infinitesimalize the area and indicate the vector delta A for that infinitesimal of area. I also need to know the electric field at each infinitesimal of area, and it turns out for this particular symmetry that E and delta A are in the same direction. So when I use Gauss's law, the dot product E dot delta A becomes just E times delta A. Furthermore, E is constant everywhere on the Gaussian surface, so I pull that out of the summation sign, and I have the summation of delta A, which is 4 pi r squared, equals the charge contained inside the Gaussian surface, and that is pi rho r cubed. Pi's cancel. E is equal to rho naught r cubed over 4 epsilon naught r squared, and that is dimensionally correct. Numerator has charge, denominator is r squared, so dimensionally correct. So that's my electric field for r greater than big R. Well, what about r less than big R? Well, for that, of course, what I'm going to do is, here's R. I need to use a Gaussian surface of radius little r, and once again I draw my infinitesimals and delta A's and E at each of the delta A's, like so. And so Gauss's law epsilon naught, once again the dot product becomes just E times delta A. E is constant, so I pull that out of summation sign, summation of delta A gives me the surface area of a sphere equals the charge contained inside the Gaussian surface. Well, that I need to find the charge that is within this Gaussian surface, which is only that part, not the entire charge. And to do that, I'm going to have to integrate. I'm going to have to integrate, and I'm going back. I'm going back up to look at right here. 4 pi rho naught over r integral of r cubed dr. And this time we're going from 0 to some fixed value r. Little notation difficulty, but I think you understand what I mean. So the right hand side becomes, and once again, r to the 4th over 4 cancels, epsilon naught e 4 pi r squared, that makes that a squared. Pi's will cancel, and so we have that E will be equal to rho naught r squared divided by 4r epsilon naught. Dimensionally correct. I need a r in the numerator, and gives me r squared in the denominator, so this is dimensionally correct. So we have an electric field, in this case, that decreases or increases for r less than big R as r squared, and then decreases outside. Okay.